All right, welcome back to the stream, and Happy New Year, everyone. Let's see what we got. We've already got Tuco. That's really how you know this stream is ready, is that the cat's in position, ready to do some electronics with you. So, yeah, and actually, this little button pad that I made in the previous streams, I haven't been sticking it on such a curved surface like I had originally planned, but aside from that, it's actually working out pretty well. And I can just stick it wherever it's handy. And, I'm starting to get more of a muscle memory for these buttons at least. Got these. These are always important. Anyway, so there's all the usual stuff. Cats are awesome. Happy New Year. 2016 is dead. 2017 is something. But despite all that, today I'm back at work on voltage glitching. So actually, this is the new board that I milled last week, and it needs to be populated. Let me first grab the board that this is replacing for a little bit of context. Oh yeah, there's a lot going on here. So this is my rig so far for this experiment. Basically I'm developing a glitch technique that should be applicable to this class of microcontrollers from TI. And this board is standing in as my kind of victim device. So right now it's just running some example code, but theoretically this could be any device with that same processor that I want to get the code off of. Then all the rest of this is kind of test setup for that experiment. So this is another of the same processor that I'm actually using just for its Ethernet interface, so that when I underclock the whole system, I get two peers on this Ethernet connection that are both speaking this non-standard slowed down Ethernet, but by having two of the same chip, I was hoping to reduce the incompatibilities so that I could slow it down as much as possible. And then the Raspberry Pi up here is actually talking to this chip. It's running like a Python program that actually implements the Ethernet interface. So it's using the on-chip debugger interface on this board to just speak directly to the Ethernet peripheral. And then I've got like a driver for the Ethernet peripheral basically implemented in user space. Then this is our old friend, the chip whisperer, and I'm using it as usual to acquire a voltage trace. So this SMA connector is just connected to the core voltage supply on this chip, the victim chip, and that's just so that I can get basically timing landmarks. So when the chip is running, I can look for waveforms that indicate what it's doing and get some idea of where things are relative to each other in time. And then since it's acting as the time reference, it also generates the clock for the whole system, and it actually generates the glitch pulses that I'm using for voltage glitching. And so it has a built-in MOSFET here for actually injecting glitches by kind of yanking the core voltage line down to ground and very briefly shorting out the power rail. But this board, I couldn't successfully slow it down quite as much as I wanted. And so the slowest I can run it right now, the core CPU clock is 27 megahertz. And the external clock, kind of before the PLL, I think it's like around 5 megahertz. So, that slower frequency is fine, but that 27 megahertz internal clock frequency is still a little bit fast for the built-in glitching hardware on the chip whisperer. So that's where I was trying to add a local MOSFET closer to the power rails here, and hopefully with a better driver. But at the time that I built this, I didn't have like a real MOSFET driver handy, so I just stuck some buffer chips on it. And it was an improvement, but still not fast enough. And then I went back and worked on this part to see if I could underclock even further. And I could get it a little bit lower, but that only really brought me down from like 30 megahertz to 27 megahertz, so that was a little disappointing. So the next step now is I'm replacing this glitch board with this new one that I just designed, which will give me a few new experimentation vectors. So the main difference is that this glitch board uses some fast MOSFET driver chips that arrived from DigiKey. So it should actually be able to generate those glitch pulses at a rate that can, kind of keep up with the clock speed on this chip. The other thing I wanted to experiment with was this actually has 3 sets of MOSFET and MOSFET driver on it, arranged in kind of a totem pole configuration. So I can use the kind of lowest one to short everything out to ground during a low voltage glitch. I can use the middle one to kind of connect the core voltage, which has an internal regulator in the MCU. And it needs some capacitance for that regulator to stay stable, but that capacitance works against you during glitching. So the middle MOSFET is just to connect that capacitance so that I can disable that during the actual glitch. And then the top MOSFET is another glitching MOSFET that I included in case I want to try glitching with a higher than normal voltage pulse. So that's the basic idea behind this circuit. We'll go to the schematic in just a sec, but basic idea is that this goes kind of as close as is practical to the physical V-core rail here. So this one was a bit in the way. I might just take this off. Well, I mean, I'm going to take this off for sure, but I might put the new board on kind of beside this or something. I didn't have this whole thing anchored down onto the wood base plate when I first put this glitch board on, so I've got a few more mechanical possibilities now. I think the first step might be to just get this off. I already actually broke one of the connections off, so that was part of the reason to just go ahead and finish the rest of this. But yeah, most of this is just going to involve cutting a couple of wires and then heating up this hot glue with the hot air gun and then just taking it off. And I can save this circuit board for other experiments that don't need quite as much speed. Oh, thank you. Somebody just reminded me that the backups need turning off. I think I've been streaming at 1 frame per second this whole time. Sorry about that. Okay, I think that'll be better. Sorry about that. I had the preferences window open on that computer to remind myself to pause the backups, but then I didn't actually do it. But planning on doing some more stream automation soon. I think my next step for trying to improve the stream quality is to just get the encoder machine on a faster CPU. I think that'll help a lot. But then after I'm done putting out frame rate and kilobit related fires on that machine, then I think my next goal is to try to get this streaming both to YouTube and Twitch. So that'll probably involve having some automation where maybe I have Nginx with the RTMP server running on one machine here, and it has some nice options so that when I start a stream to that machine, I can have it do transcoding and rebroadcast it, but I can also have it run shell scripts. So I could probably find some way to automate turning off the backups here. Yeah, that was a good suggestion. I need a pre-flight checklist like pilots have for these streams. That probably would be a good idea. I feel like I have this kind of mental checklist that I'm running through already. Okay, restart OBS, because if OBS has been running for too long, the audio will be out of sync, and got to turn off the backups, and got to make sure the audio levels are fine, and got to make sure that the all the video interfaces are still running and haven't crashed. So, yeah. And I don't know how much of that's going to change when I kind of redo this setup yet again for the new computer that I ordered. Because right now it's running on this Mac Mini that's just barely fast enough, and I'd been meaning to throw some more hardware at the problem. So thanks in large part to my generous Patreon supporters, I was able to get a new computer to run the streams off of. So, and not just a new computer, but also I needed a new capture device because the capture device I was using was Thunderbolt. So anyway, some hardware will be arriving soon that should let me do higher bitrate 1080p streams, which I'm excited about. Because I don't think the limitation right now is my ISP. I think it's totally just the CPU on this Mac Mini can't keep up with all the, all the compositing and compressing and decompressing and deinterlacing and all that it's doing. All right. Anyway, I think the stream is happy and the cat is happy, so let's get back to work. Maybe put a anti-static strap on for this thing. When I'm just working on like little Arduino stuff, I often don't worry about anti-static straps because they tend to have pretty good ESD protection and the cost of failure is not especially high. But when you start working on stuff you've put a lot of time into or that has some static sensitive inputs, it's a really good idea. I really need to avoid hair cam. So this wire was my clock signal. I'm just going to temporarily move that out of the way. And then I had these thick wires for grounds and for the actual core voltage. And then these thin wires over here for power, which I can probably keep a lot of that wire. And I was using 3.3 volts as the kind of main logic voltage, and then 5 volts to run the MOSFET drivers. And I think I'm going to keep that same basic strategy, except I have a jumper that lets me replace the MOSFET drive voltage if I want, so when I'm doing high voltage experiments later, I might end up needing a higher MOSFET drive voltage. I'll show you on the schematic, but since it's all N-channel MOSFETs, the gate voltage has to be, at least a few volts higher than the voltage you're switching. And normally that's fine, because this CPU core is like 1.2 volts, so switching the MOSFET gate with 5 volts seems to cover my bases all right. But if I want to experiment with higher CPU core voltages, then that'll be a problem. Yeah, it's just held on by that little bit of hot glue in the jumpers right now. So I'm going to heat that up gently. Nice. Clean removal. Well, kind of clean. I think I damaged some of the circuit board pads when, so I mentioned one of the wires broke earlier, and I think I pulled off like a ground pad, but I don't think it was one that I really needed, so I'm not too worried about that. I think this is reaching the limit of what this camera can do, so maybe we switch to the microscope. Microscope. Which one is the microscope? Not that one. All right, I for microscope. Clearly. This is when you just get to see me rummaging. Oh, this is the microscope. It just doesn't look like much because I don't have anything under there. That is this one. Great. I'll remember that eventually. So. So I had already done a few weird modifications to this board for earlier experiments. Let's see if I can try to clean this up a little bit. That was from an experiment I did earlier where I put some series resistors in with the Ethernet and then, and then replaced them with copper tape after I had done the experiment. I also took off the capacitors from the core voltage. Okay, there's the damaged pad. So those two lower pads on C14 and C15 were both going to ground through a via, and I think I just totally yanked that off. This thing that's sticking up here is V-core, so I want that. I think that might also be the same as the other pad on some of these capacitors, so let's try testing that out just to get our bearings. I mean, I have a schematic for this board also, but sometimes just using the multimeter is faster. This one. There are two identical circuit boards, and the DSLR is pointing to the wrong one. Of course, the microscope is hogging the best location. Oh, maybe that's all right. Okay. Yeah, these were both V-core capacitors that I removed. And I think this was like a 3.3 volt capacitor over here. So these capacitors can stay gone, and I don't really need to repair these pads, but I should find another ground that's close by. So I think one of these would do. Okay. So it looks like I can just use these two pads, and that'll give me a nice direct path to the processor. Because really I want to really reduce the resistance and inductance of the wiring between the glitching board and the processor to get the fastest edge. So I don't think that needs any additional cleanup then. I think we can just go ahead and assemble the new thing. And then that's where we attach it when it's done. All right. Oh. Just catching up on chat, and I saw some comments about blowing up boards by powering them through their I/O pins, and that might be even easier than static. And yeah, I have to agree with that. It's certainly disconcerting when like you thought you unplugged your dev board and the power LED is still on, and it's like, oh, that's not good. And then you unplug everything else and try to track down what was causing it. Because it's, I mean, you know, it's not necessarily going to damage anything, but it sure is operating the chip outside of spec, and it certainly can damage things. All right, so here's the board. I think we're actually going to go to the computer next to look at the schematic, though, before we do too much with this. It's got these big areas over here for the MOSFETs, and then in the middle here, the MOSFET drivers are in SOT23-6 packages, and then we have one of these little buffers in an SC70 package. And all of this was done on the other mill just with the 80-degree engraving bit. So you can see that the way this was set up, it made kind of one pass on each edge of the outline. And then some places it kind of left this really thin sliver of copper. So that's something we have to kind of watch out for, because that can make conductive debris. But yeah, let's go to the schematic before we get too deep in this. All right. CAD. Okay, here is the schematic in KiCad. So it has a few new features relative to the last one. So as I mentioned, it has these 3 MOSFET stages. So these 2 terminals are intended to go to the ground and core voltage on the target processor. And by turning on these 3 different MOSFETs, we can either have it in normal operation where the core voltage rail is bridged to this bank of capacitors to help stabilize its regulator, or we can have a low voltage glitch where we short it to ground, or we can have a high voltage glitch where we short it to this other bank of capacitors that we can charge to a higher voltage with these headers. And then each of the MOSFETs is driven by this same driver, an LM5134, which is one of the faster ones that I could find on DigiKey. Got a few test points. And what else? Oh yeah, so I have these jumpers here so that you can selectively enable either the high voltage glitches or the shorting glitches. And those just take advantage of these secondary inputs that act like an inverted input to an AND gate. So these have a truth table such that their output is high only if in is high and in B is low. The B just stands for inverted here. So by using that, I have this set up so that this rail here is our kind of conditioned glitch trigger pulse, and that's normally low, and when this goes high, then I can turn on this MOSFET driver, but conditionally on this jumper being placed. I can also turn on this MOSFET driver conditionally on this jumper being placed, and I always turn off this MOSFET driver. So during the glitch, I just temporarily disconnect those stabilization capacitors. And then this little circuit is just made up of the, with that one little dual Schmidt trigger buffer or inverter chip, and it tries to clean up the input pulses coming from the other end of a long wire. It also has a really small just a really basic kind of high pass filter here, so that if the glitch input gets stuck high, then I don't actually end up getting the transistors stuck on. So this is a relatively large capacitor relative to the signals we're working with, 0.1 microfarad. So at this scale, the pulses we're working with go pretty much straight through this capacitor unaffected. But when it kind of settles into a stable level, this fairly high value resistor of 47K will end up charging this side of the capacitor up to 3.3 volts, which ends up setting kind of the default state of this output to 0. And that happens over a time scale of like several milliseconds, which is much longer than the glitches we're going to be working on. So that's just a bit of a safeguard against the transistors getting stuck in a state which just short circuits the regulator, which is something that I occasionally have trouble with. When I give the chip whisperer some value that's out of range, it will sometimes just leave the output on. I think that's pretty much it. Just a few more power supply capacitors and 3.3 volt and 5 volt inputs. Let's go to the schematic or the PC board. Is this it? And then the PCB layout is double-sided. Tried to keep very few things, very few things on the backside, and it's mostly just, laid out pretty straightforward on the top side here. And a lot of the spacings are set by this SC70 package, which was the smallest thing on this board. So I also tried to make this fairly friendly for hand assembly. So I didn't put things super close to the very tiny surface mount components, and I didn't put any vias under chips, because that that makes assembling a non-plated through circuit board much harder, because you have to be very careful about making the vias really flat. So this should be pretty straightforward. I'm going to start by just plugging the vias with some wire, and then we can start putting on components. Well, actually, first I'm going to start with just a little bit of electrical testing to try to rule out any obvious shorts, but then setting up vias and soldering on chips. So Okay, so I'm just going to do a really basic test by putting one probe on this copper fill out here, and then just looking for stuff that's connected to that really shouldn't be. So I think I made this board with such a generous spacing that I wouldn't expect to see shorts, but these little slivers of copper can get into unexpected places pretty easily. Seems good so far. Let's take a quick look at the other side. The other side is pretty simple. There's some dangerous looking bits of copper there. I think this little critter. It's not shorting anything out, but it is dangerous. So some of these I think I could take off by like lightly sanding the board, which I might do next. Should also be nice to clean up the edges. So yeah, that helps remove some of those very weak pieces of copper that are barely hanging on, because you really don't want those coming off later and shorting something out. And then it's nice to clean up the edges. Somebody suggested before that I really should have rounded the corners on my boards, and I usually maintain that when I'm just making like a one-off prototype, it's easier to sand it than it is to actually round the corners in KiCad, but maybe that's just because I don't know the right trick for rounding corners on drawings. I have to admit it was really nice when I made that flexible button thing. It was nice being able to design the circuit board perimeter in Rhino and then import it into KiCad. Like the DXF file import output is pretty nice. Okay. I think that's all the fussing with sanding I'm going to do right now. So yeah, not quite as clean and pristine a surface, but I think it's a bit more functional. It should be a little bit easier to solder to on account of the scratching up any small bit of oxidation, and it should make for less of this dangerous conductive debris. Not entirely gone, but less of it. All right. I think it's via time. Get some thinner bus wire. I got some new wire just for this kind of stuff. I kept having to strip the insulation off of my 26 gauge wire. This is a roll of uninsulated 28 gauge. My goal here is just to sit the wire in there any way that it doesn't fall out and doesn't really short anything, and then solder it on both sides and then trim it. Seems like a decent size. I forget what the actual via diameter was in KiCad. I think it was the default. Like, I know I checked it against my drill size because I like to do vias with a 1/64 inch drill. And I think the default via size was a little bit bigger than that, so it already worked out pretty nicely. Oops, lost that one. Let's put another one in after it. 2 more, I think. Cool. I think that's all of them, until one falls out, I guess. All right. Get soldering time. Oh, I have way too many kinds of wire at the desk right now. All right. Oh, that's a via. I forgot about that one. Wire. I should probably just go ahead and add a bunch of flux. I think that would help with all of these connections. It's not quite as spread out as it needs to be. Ah, that's not what I wanted. Ah, this flux is so thick. I suspect it would come out of the syringe a little easier if I warmed it, but don't know if that would be good for its shelf life. Oh, another one I missed. That's nice. I hope everybody who wants to has been getting a chance to watch the talks from CCC this year. I've been watching a bunch of them so far, and it's really good. I should actually make sure I can go next year. I've been wanting to go for many years, but I haven't actually made it happen. There's nice, there were a couple of talks on video game hacking, which is kind of an old hobby of mine. Not something I've really done in a while, but it's nice to see some familiar faces and see some new exploits and new research. Oh, I also really like seeing the new research from the Osmocom folks on one of the Qualcomm basebands. They were getting kind of further inside. That was pretty neat. I've poked around in those basebands just a little bit, but not nearly as much as those guys have, and it's really nice seeing what they've been able to come up with. What is going on there? low on wires here. A couple more, I guess, but almost ready to flip this over. I think the wire kind of laid down perfectly and got stuck to the track right there. Yeah. I don't actually want it to get that stuck because I kind of want to trim that, but I guess it doesn't matter that much. Alright, I guess this is ready to be flipped. Yeah, that side looks good. Let's get this side kind of fluxy and start soldering it. Scrooge. I often imagine that this part, like, must be the weirdest part of PCB assembly to people who don't know what's going on. Just like, I thought this was electronics. It looks like you're covering that board with alien snot. What's going on? But so much of electronics is just like covering things with weird chemicals. Like, I actually used to live pretty close to one of the famous kind of Superfund sites in Silicon Valley where there were giant kind of environmental messes that previous semiconductor fab companies had left there. I wonder how much that would be different if, you know, if we were actually serious about doing semiconductor fab in the US again. Like, I wonder how much that was a climate of things being new and not regulated yet, and how much of it is just, like, always going to happen to some extent. I guess there are still semiconductors being made in this country. I just don't know much about them. And they seem like a pretty small minority of all the semiconductors out there. Some of these would have been a little easier to solder with thermal reliefs, I guess. With this much flux, the solder just wants to keep spreading until the wire actually heats up, I guess. Pads on this side of the board look kind of weird because it's where there are all those MOSFETs in SO8 packages, but then for some of the most important signals, I have polygon fills instead of regular traces. So like this is where a MOSFET sits, but you can only mostly see the gate pin because the source and drain are kind of covered up by polygons. When the solder really prefers to stick to the ground plane or to the kind of extra copper instead of to the actual wire. Just spread that out. I wonder how hard it would be to do hot air solder leveling finish at home. I'm not going to worry about this extra solder on some of these capacitor pads because like the first step on soldering those will be to put solder down on one of the pads anyway. Okay. Oh yeah, from the chat, TSMC has a fab in the US. That sounds like one of the ones that I had heard about, but I wasn't sure where it was. Apparently this one is Wafer Tech in the lovely state of Washington. That's pretty neat. I still kind of dream of the at-home wafer fab. You know, I think that'll be, I mean, a little bit like 3D printing has been for mechanical structures. Like finally people will actually be able to make electronics instead of just putting together electronic building blocks at home. That'll be pretty neat. I'm sure there are a lot of physical realities to come to terms with in terms of making a really small chip fab. What would it be like to have like an easy bake oven for chips? Like, you know, all the ingredients are in little packets and you can just follow the recipe and make a 555 at home. I'm wondering if maybe some of the really caustic cleaning and coating steps can be done like separately. I mean, the machine comes with this like pre-cleaned compartment that you can load wafers into and then etch them. Or maybe there's something kind of in between an FPGA and you know, a full ASIC, where you can buy wafers that are pre-patterned with a bunch of little logic units, and then you can etch the metal layer to connect them. Actually, that sounds familiar. I wonder if that was like something that used to be popular. Oh, I think this via is not in amazing shape, but maybe it's fine. It's starting to get difficult to see which ones are actually still in need of work. Yeah, there's a couple left near the top here. Vias. Yeah, I often leave out the thermal, you know, if you've seen like the little kind of cutouts that often happen around pads to isolate them from the plane that they're around. I didn't include those thermal cutouts on this board because I tend to just get annoyed by them when milling. But for the ground plane here, they might have helped. One problem you might encounter with non-plated through holes is that the solder would really much rather stick to the surrounding areas of copper than to the entire ring around your wire. So it's possible that might be better if I was using thicker diameter wire. I think this is 28 gauge, and sometimes, I think last time I used 26 gauge, and that might have worked a little better. But I mean, that's not really a huge deal. I mean, it'll still work, but it will make your vias more susceptible to breaking if it doesn't form a nice full ring. And right here you see so much bubbling, which is all the flux kind of in that hole, kind of outgassing as the whole thing heats up. Which also seems to be a little different when you don't have a plated through board. Okay, I think that's all of them. Let's take a closer look. Well, there's one I missed on the right there. Oh, this is so not focusing. No, let's just put it back on here for now. Yeah, just that one, I think. All right. Now that I'm looking at this under the microscope, my cutters are filthy. Let's clean them first. Yeah. It's really important to only cut one of these at a time. If you accidentally get two, then it'll just wedge both of those pads right off the board, most likely. I mean, it's less important if you cut one that's already detached, but it's still better to only cut one thing at a time. Boogers. All right, I think all the vias are trimmed on this side. Next side. I'm not going to clean the flux off. We're just going to be adding flux at this point. That one looks suspect. It's a little dangerous to reheat it at this point since the other side is so little, but I'm gonna try it, and if I have to redo this via, no big deal. I think that worked though. Let's check the other side. Yep, cool. A little bit of cleanup, but I think we've mostly gotten those off now. Alright, I could potentially clean the backside now, but I think enough cross-contamination is going to exist between sides that I'm not going to worry too much about that now. That one might could use a touch-up. Okay, I think it's time to put, time to put some chips on. I mean, I guess I could also do these 0.1-inch headers just to get that finished up. But then everything else on here is surface mount. Headers. Peaceful cat. Alright, just have 5 of these little 2x1 jumpers. Some of these are for connecting external equipment, and some of them are for shorting jumpers. But it was a convenient form factor. And also for convenience in home manufacturing, I made it so that these don't need to be soldered on the top side, only the bottom side. It's possible to solder these on the top side, but very annoying. Let's see, there's a bunch of ways to stabilize those. I think the easiest might be to just plug it into a little breadboard. Alright, little breadboard. I can just line them up, press them on. Flip this whole thing over. And then this still doesn't quite sit flat, but like you can hold it and kind of feel where flat is supposed to be. And then you can kind of prop this up a little bit with something. And then find actual flat. And then solder the rest. It's a really good thing these cat hairs are not conductive. Nor do they really seem to mess with the solder surface tension much. There's the top of our board. There's the bottom. So now it just needs a bunch of surface mount stuff. So I think first I want to put down the MOSFETs. I mean, there are a lot of different strategies here. You can start with the MOSFETs because they're kind of big landmarks that are a little bit weird to place on this particular board. You can start with this inverter chip because it's the smallest. Doesn't really matter. I think I'm just going to do the MOSFETs first. I got 3 of these. Always good to double check pin 1 on the diagram. Yeah, so we have these 3 MOSFETs, that one, and that one. And they're all lined up the same way with pin 1 on the top left. And pin 4 is that gate, which is the one that goes kind of its own place. The other ones are all combined. So, let's start by maybe just putting a little bit of solder on that gate pin and then using it to line up the whole rest of the chip. And also flux before we do anything else. Alright, that'll do for now. Right. 3 of these little chips. Oh, pretty big actually. SO8 seems kind of enormous. High power MOSFETs. I'll have to try another good flux recommendation. So this is MG Chemicals, which one is it? 8341. And yeah, it's like a gel in a syringe, which seems to work really well for kind of crazy surface mount parts. I've also used these flux pens quite a lot. This is Kester 2331ZX. Yeah, and I like that for situations where I need less flux, but this recommendation is for Kester 951, which I guess is a thinner liquid that you can drop on. It sounds nice. It's really hard to see the markings on that chip. There we go. So, pin 1 on the left. Oh, this used to sit really flat, and now for some reason this is rattling. I'm not quite sure what happened. Ah, there's a bit of junk on the bottom of this. Oh, that's so much better. Okay. Don't mind me. That seems fine. Well, I guess this is what really tells us the proper kind of horizontal position, is that this pin 5, needs to fit on that little rectangle. So actually that'll tell us how to line up the other chips, because they all should form a straight line vertically. So just about like that. Seems about the same place I put the other chip. Yay, consistency. Okay, so on each of these I have one corner tacked down, and I've done my best to make sure the chip is lined up and level, and now I'm just going to add solder to the other pins. And SO8s are so big that it's pretty much always practical to treat all the pins as kind of individual entities. So you don't really have to do kind of drag soldering or kind of play with surface tension to get these soldered. If you're looking to practice surface mount soldering, I have to say SO8 MOSFETs might be the most forgiving part, because they really only have 3 pins. I guess it's kind of like my experience with BGA parts and embedded MMC flash memory. Because they usually come in BGA packages, but they only have like maybe 10 actual pins connected, even if they have this big grid of balls under the package. Alright, big old transistors are on. Let's do some more semiconductors. So these 3 positions are for the 6-pin kind of SOT23 style driver chips. They all seem to be the same orientation also. And if we look back here, we can see that these have pin 1 on the bottom right. Yeah, so they're upside down relative to the MOSFETs. Man, MOSFET drivers are such interesting little special purpose parts. I seem to remember seeing some projects that used MOSFET drivers as, not to drive MOSFETs, but actually just as direct drivers for some other kind of small load. Which seems interesting. Oh, wow, where is pin 1 on this? I'm gonna have to look at the data sheet. I assume pin 1 is bottom left right now. But maybe we look at the data sheet. LM5134. Well, there's supposed to be a pin 1 marking. Well, oh, I guess that little raised bar is pin 1. Anyway, I think this is the right orientation. So that would be pin 1, 2, and then 4 is ground. Yeah, that seems right. All right. More like that then. Cab. These package markings are so strange. Yeah, usually the data sheet has a section that indicates what the package markings are. I'm not seeing that here. Ah, here it is. Device marking, SK7B. Great. At least it's the right device. Or at least the counterfeiters marked it correctly. I should set aside time today to take a walk and get a sandwich. That would be amazing. Walking and having a sandwich in the same experience. I mean, I guess there would first be a walk without sandwich, and then I could walk and eat the sandwich if I wanted. Or I could make a sandwich here and walk with the sandwich. Clearly that's the solution. Except I'm out of bread. So I have to leave the house to get a sandwich no matter what. Unless I have a sandwich delivered, which seems silly. Because there's a sandwich place pretty close by that I like, and I want to walk anyway. This is what I think about when my cat's asleep. When he's not filling my head with dreams of nylon bolts. Really, I just want sandwiches. Okay, I think these parts are on. What's next? I eat things that are not sandwiches sometimes. I like sandwiches though. I had soup the other day. I'm not especially good at, you know, keeping myself comfortable, but it's nice when I have friends that are much better at that. My friend Zach was a professional chef for a couple of years, and so I still feel like every time he touches food, he can just like make it turn into delicious magic. So I had some soup leftovers that he made for Christmas. That was really nice. But mostly when it's up to me, I make, like when I'm in the mood to cook, I really like making like basic tofu curry kind of dishes and throwing vegetables and rice and that kind of stuff. All right. Let's put on this really tiny chip now, and I think everything else is passive components. So we've got some resistors and a bunch of capacitors, and this little critter. Let's see. Right. All right, pin 1 on the top left. These are the things you have to look up when you don't have silkscreen markings. All right. Oh man, sandwich printers. That seems amazing. I mean, we're kind of working on, I don't know, there's all these structures that I guess you could describe as computational foam, where you make these kind of mostly open structures with 3D printing. And clearly that's just one step away from bread printing, right? Whoa. I don't know if this is the right part. Because this one's in a SOT 23.6. All right, I think I've got some faster inverters that are in an SC70 package that I need to find. Welcome to my highly organized empire of surface mount components. These out for the purposes of this project. Maybe I already got it handy, so now I can't find it. Oh, here it is. Yes, so convenient, I misplaced it. What's up, Tiger? Aw. Alright, so these are fairly fast dual Schmidt trigger inverters with a pretty wide voltage range. It's the NC7WZ14, which is basically 74 series logic, like the 7414, but it's like its own logic family for these really tiny things. Alright, now this little tiny thing. And again, adjusting the light so I can see any of it. And pin 1 is on the top this time. All the extra flux here definitely helps. Like that kind of helps the solder just level it out, or level itself out so that it then makes contact with all the important areas. Of course, then I keep sticking my finger in the flux and getting my finger all sticky. I was really trying to give Tuco an area of my hand to lick that I was pretty sure I hadn't gotten flux on. Did I move some of this solder? Not entirely. Okay. That should do it. So that's all the chips. Alright, this is the one. So it's a little hard to tell what's what among these pads. These larger ones are test points, or spots where I plan to solder wires to the device under test. But then some of these I'm not going to populate yet. Like, I'm going to leave out all of these capacitors, I think, or maybe just populate like 2 microfarads worth. And then down here I'm going to put in 2 microfarads. Because that's all I think I need to keep the regulator stable. I might put in like 3, but these are somewhat, you know, I put these here partly to have reserved space for extra capacitors if I need them later. I guess that's a resistor. There we go. 47K resistor, 0.1 capacitors, another 47K. So maybe we'll just kind of do this left to right-ish and start with the 0.1s. I've got the obligatory giant roll of 0.1 capacitors. Oh, Tuco's way over there now. Okay, it's kind of hard to read. That's a 0.1 on the bottom and then a 1 microfarad on top. Hey, cat. Tombstone. Tuco was climbing on the heater and then it just turned on. I think he's going to realize it's getting warm pretty soon. So that's another 47. What else do we have for 0.1s? These two capacitors. Oh, these three. Okay. So that's the next spot. So these capacitors are providing the, well, these in combination with the 1 microfarads that I'm going to add are going to provide the little bit of local energy store to help the MOSFET drivers deliver this fairly large pulse of current that they need in order to charge the gate of the actual MOSFET. Oh, Tuco's back over here. Okay. So that was 4.1 caps. Let's check the schematic. So that was this one, and those three. So this one, C3, is also 0.1 microfarad, and then I think the rest of them are 1. And C3 is this one. Okay. Maybe use some resistors. We also had a bunch of these 47K resistors. Yeah, and these are in a bigger package. I hope they fit. I didn't think I realized they were in a bigger package when I designed this. These are 805. This is a little bit oversized, so I'm going to have to solder it carefully. It's not too bad. Just catching up slightly on chat. There's one question about what size solder tip I'm using. I think this is a 1/64th inch. It's whatever the smallest one that Weller makes for this iron. And I do use hot air. I use hot air and solder paste for assembly sometimes. Solder paste I'll generally use when I want to assemble the whole board all in one go, and usually more when it's when the board has solder mask on it. So I don't find solder paste quite as useful for boards that are not plated through and don't have solder mask, because, like, for example, this board, I couldn't just stick it on a hot plate because of the DIY vias. I could potentially do it hot plate before adding the vias, and then add the vias manually with a regular soldering iron. But yeah, I guess when it's a board that I'm doing just kind of like a one-off production without solder mask or plated through vias, then the solder paste hot plate method doesn't necessarily seem faster to me or necessarily more reliable. But yeah, I've definitely done a bunch of boards with hot plate and solder paste when I was doing, like, kind of making dozens of those fade candy boards myself. Let's see, a couple more 47K. Let's want that. Yeah, those two. Okay. I think the 1 microfarad caps are probably next. Start over here. Yeah, I'm curious if solder paste plus hot plate would actually work pretty well if you had a really nice stencil. So that might be something to try if, you know, if I'm still making boards at home in the future when, like, I've been wanting to get a laser cutter for a while, and if I actually make that happen, then I might be able to do stencils at home. I could try doing stencils with the mill. I think a lot of that would depend on finding just the right material, but maybe that would work. Like, I mean, if I can mill flexible circuit boards, then maybe I can mill like Kapton stencils. Okay, these 3 caps are 0.1 or 1 microfarad also to provide some energy for the MOSFET drivers. I think I'll probably wrap up this stream after getting this board assembled and go for my sandwich walk before testing this. But I might be able to stream the testing too if folks are interested. And I mean, I was thinking about how to test this. I mean, I could test it on its own. I could also just test it with the microcontroller attached, since part of what I wanted to test was how well this helps the regulator stay stable when we're not glitching, but then helps get those capacitors out of the way when we are. And I don't really have a reason not to just hook it up to the target, but if I needed to test it in isolation, I'm sure I could just hook up some other LDO regulator to it. Then some capacitors over here. Yeah, this kind of unmarked area over here is where I can put capacitors. So that's ground. Okay, yeah, that's ground. That's the glitching voltage. And then this is the kind of normal voltage that it connects the capacitors up to when we're not glitching. So let's just put like 3 microfarads worth of capacitors there, because I think the datasheet recommends 4, but I'd been using 2 before, and that seemed like kind of the bare minimum. But I don't think I have to cut it quite so close with this setup disconnecting the capacitors, so let's try 3. Cat hair composite. The highest quality cat hair solder fiberglass composite boards. These aren't even fiberglass, but whatever this stuff is, like paper or epoxy or whatever. I forget whether this is technically FR1 or FR2. Like, I think it was sold as FR1, which I thought was like actually made of paper, but it acts a lot like epoxy. So I don't know. Probably just paper with a lot of epoxy in it. Well, I think this is ready for some cleaning. I think that's all the soldering for now, until it's time to install this thing. I know this is just going to move the sticky mess elsewhere, but I think most of it's just going to end up on this glass plate, which is easy to clean. Bubbles are kind of interesting. Well, thanks for tuning in for some circuit fabrication with me today. This is a nice little doodad that I hope will do what I want and help me get some firmware out of this chip. But yeah, it's nice being able to just put together prototypes at home and try out ideas pretty quickly. And like that's something I've always done, you know, ever since you could still buy like decent electronic parts at Radio Shack, and I would just put stuff together on proto board. But making circuit boards is certainly nice, and it helps a lot with these kind of not just the small surface mount parts, but also these very fast signals that I'm trying to work with here. It's nice to not have breadboards and fly wires all over the place. Looks like Tuco's pretty peaceful. I would pet him, but my hands are still covered in flux, so I think I need to wash them pretty well before getting my sandwich or playing with my cat. Anyway, thanks so much for joining. I think that ends it for this stream, but there'll be plenty more. If you want to be sure to catch the next one, I tend to announce them both on Twitter with the little automatic YouTube announcements, and if you click the little bell notification thing on my YouTube channel, then it'll send you notifies when I'm doing a stream, so that's another way to keep up. But thanks again, Happy New Year everyone, and I'll be seeing you all soon.